counseling, stuff like that. Okay, so this is the 11th lecture of probability. Okay, we are now in a transition moment. Okay, this is like the inflection point lecture. We've now finished our emphasis on combinatorics. We're now going to move to random variables, to densities, and this now means we have an exam. So I will give you the exam on Wednesday. You will have 1 week to do it at your convenience. I'll give you more information either today or tomorrow on the mechanics. So we're now in a new unit of material. So what I want to do is I want to talk about probabilities of events. I'm going to have random variables, and the variables are going to represent different quantities. So probably one of the most common examples is toss 3 coins. And maybe we'll say the tosses are independent. And xi is the outcome of the ith toss. So I'm writing my variable x like this with the big lines over it. In a lot of textbooks, they write it like this in bold. The point is for you to just realize that it's a capital letter and it's a random variable. You want good notation. We've talked about how bad cosecant is, because cosecant makes you think of a connection with cosine, not with sine. I actually know a mathematician who refuses to use bold in his research papers because you only use bold when you're writing on a blackboard or something like this. I will just use a capital letter with lines over this so you can quickly look down and see it's a random variable. So if I toss a coin, what are the possible outcomes? Heads or tails. Do we all agree that if we toss a coin, we're going to get either a head or a tail? Okay? Assuming it's a standard type of coin. One of my skills is actually I'm in charge of the soccer coin tosses for my son's team. We have yet to lose a coin toss in all these weeks. But I don't really want to represent the outcome of the tosses as heads and tails. Any idea why I don't want them to be heads and tails? They're not numbers.
So it could be like 0 and 1?
So you'll do 0 and 1 typically. Sometimes, to be different, you'll do -1 and 1. And depending on what you're doing, that could be useful. Maybe a head is you take a step in this direction, and a tail is you take a step in the opposite direction. So if you do something like that, you would want a 1 and a -1. We want our random variables to have real values. Or maybe complex, but random variables to have real values. So here, a head will be a 1, a tail will be a 0. You could, of course, do it the other way, but then you would be violating almost every math book in creation. So make heads 1, tails 0. And the advantage is you can combine. What's 2 heads and a tail? How do you add 2 heads and a tail? What do you get? Well, if I convert like this, I get 2. But if I have 2 heads and a tail, all I can say is I have 2 heads and a tail. I can't really combine them. This is why we like to use numbers. Okay? It allows us to have random variables combining with each other. What is the probability that xi equals 1? Yes? Good question. So if I don't, well, the coins are all being tossed independently. But I haven't said what the probability is. So if it's a fair coin, it would be 1/2. In general, we might say the probability that we get a head is p, so then the probability that we get a tail, which is 0, would be 1 minus p. If p equals 1/2, we say the coin is fair. Okay? Similarly, if I roll a die, the possible values for the die are 1 through 6. The die is fair if all numbers occur equally likely. We could create a new variable. X could be x1 plus x2 plus x3. The sum of those. What would this random variable represent? So what would it represent? Yes?
The number of heads after 3 times.
Sure, good. So this would be the number of heads after 3 independent tosses. And what we're going to do now is we're going to see a little bit of a precursor for later in the semester. We want to try to figure out what is the distribution, what is the probability of the different events. So what are the possible numbers of heads we could get? 0, 1, 2, 3. So what we want to calculate is what's the probability that x equals k? Any thoughts? Yes?
Count up all the ways when x is k and then divide it by like anything else, everything that it could be.
Okay, so one possibility is we could count out how many ways there are to get exactly k heads. And then we could divide by the total number. That assumes all outcomes are equally likely.
Oh, yeah.
So if the coin is fair, then you can use this counting approach. And we can count how many ways are there with exactly k heads, divided by how many ways are there total. There's there's 2 cubed ways. And if the coin is fair, we can just do that by counting. Unfortunately, if the coin is not fair, it's a little bit harder. But what's nice is all that matters is we choose k of these tosses to be heads. How many ways are there to choose k of the tosses to be heads? And choose k. And so we can do it in general. And now, what's the probability that we have exactly k heads? P to the k. I'm going to just do this carefully. There we go. Hopefully that will display. Yes?
Shouldn't we also know that there are like n minus k not heads?
Yes. And so now we need to put that in over here. And now what's the probability that the remaining ones are all tails? There would be 1 minus p to the k. To the n minus k, thank you. And so this is the probability. Now, you should really write a little bit more. You should say 0 less than equal to k less than equal to n, an integer. You always want to know where can you use a formula. Amazingly, this formula will work if k is an integer larger than n. So what do you think 4 choose 5 should be? How many ways are there to choose 5 people from 4? 0. Yes. Yes, it's 0. So it turns out that when you look at the extended definition of this, you get 0. Okay. So the idea is, in a situation like this, we already know enough combinatorics to calculate something like this. And there's a lot of situations where we will have distributions like this. This distribution is extremely important. It has a name. We say this is x is binomial with parameters n and p. So n is the number of tosses, p is the probability of success, and bin just means binomial. And it seems like there's a theorem lurking in the background. Over here, for these, we would say these xi's are all Bernoulli with probability p of success. And there seems to be a theorem that if we sum independent Bernoulli random variables, we're going to get a binomial random variable. Which do you think is easier to analyze, tossing one coin or tossing many coins? Tossing one coin. So one of the big themes of this part of the course is how could we take knowledge of one toss and combine this and get knowledge of what's happening with multiple tosses. As n and k get very large, this distribution becomes harder and harder to work with. Fortunately, it actually is converging to being approximately normal. And this is the central limit theorem, which we will spend a lot of time on that later. So we're going to look at lots and lots of different probability distributions. Okay? So here's the setup. We have some space, omega. We have a sigma algebra of subsets where we can assign probabilities. And I never want to say that phrase again in this course. All right? So just imagine we are restricting ourselves to a subset of events which we can assign probabilities to. We are not allowing ourselves to assign probabilities to all events, to all subsets. We are allowing ourselves to assign probabilities to events that we care about. Probabilities of intervals, of circles, of squares. Okay? Things like that. And now what we want to do is we want a probability function on the elements. And so I want to try to use the same notation in the book. Okay, so we say x is a random variable if it is a real valued function from sigma algebra to the real numbers on sigma algebra. So if omega is countable, or at most countable, things are very nice. What we can do is each omega in omega gets a probability. Okay? In a situation like this where we don't have uncountable things, we're fine. And now we wanted to find a random variable. And so we would take x, we would put in omega, and we would get some real number. So for example, maybe omega is the set of all three tosses. You know, head, 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 tail, all the way down to tail, tail, tail. We have 8 elements. We can assign probabilities to all these events. If we have a fair coin, what's the probability of all the events? 1/8. Anybody know what the Mobius coin is? Has anybody heard the phrase Mobius before? Yes. Where have you heard Mobius? The Mobius strip, which only has one side. You fold it in on itself. The Mobius coin is wonderful for probability problems. It only has one side. So when you toss the Mobius coin, you always get a head. What would be the probability of these events now? Yes? For all of them? The first one would be 1 and everything else would be 0. So depending on how I assign probabilities, the probabilities of the events in my space can differ, but the underlying space is the same. And now what I can do is I can talk about random variables. So the random variable might count how many heads there are. And I could ask, what's the probability x equals 3? So if I have the Mobius coin, so Mobius coin, what's the probability my random variable x takes on the value 3? 1, because I always get heads. If I have a fair coin, what's the probability that I have 3 heads? It would be 1/8. Excellent. So the answer for what the random variable will be will depend on your situation. Okay? And I want to understand how my variable, what's the probability it takes on different values, depending on how I assign probabilities to events. Okay? And this idea of tossing coins, this was used for many years to model the stock market. Maybe the stock goes up, hopefully with a positive probability, so maybe it's a biased coin that's more likely to go up than down. And then you might ask, if I, say, have a 60% chance of going up and a 40% chance of going down, over time I expect my prices to be drifting upward. How rapidly do I expect them to drift upward? What range do I expect them to be in? These are all questions that we can now start to solve using things like this. So what we want to do now is we want to introduce a probability density function. A lot of math textbooks go through everything for discrete random variables, and then they go through everything again for continuous random variables. There's really not that much difference between continuous and discrete. In discrete random variables, we have sums. What do you think we have in continuous random variables? Integrals. And I think I've mentioned this before. Is there anybody here who has taken a class in advanced summation theory? Okay. Anybody here taken a class in integration theory? There should be more hands going up right now. Calc 2, even the visiting high school students I think have taken calculus 2. Right? Calculus 2, who's taking calculus 2? areas under curves, right? We found areas under curves. The reason we care about areas under curves is areas under curves give us probabilities. That's why we spend so much time learning how to integrate. Now, does anybody know the big lie from Calc 2? Yes?
Most functions are integratable?
Yes. So in Calc 2, you find out, oh, I can integrate this. Oh, I can integrate this. I can integrate this. Oh, this problem is hard. Oh, here's the solution key. That's what I could have done. Okay. So in Calc 2, essentially every problem you get has a nice answer. It's because your teachers work hard to make sure they give you functions restricted to a certain class where the integration can be done nicely. In the real world, most of the time, this is not the case. Fortunately, there's a large class of functions where we can do the integrals in exact form, and these are flexible enough that they do a really good job of modeling things in the real world. So there's an official visiting day, I think it's October 28th, and so I will give a lecture on applications of multivariable calculus and probability to baseball mathematics. And it all comes down to I need to find a couple of distributions that do a good job modeling things in the real world. I actually just gave a variant of this at a hockey conference in Boston this weekend. Was there a question? So, while Calc 2 is somewhat of a lie in that you feel that you can do all these integrals, it's not a horrible lie, all things considered, because the integrals you can do are at least a wide enough class of things to be useful. And they do a wonderful job of modeling the real world. They also give you the opportunity of trying to have a closed form exact answer. If you have a nice answer and you want to know, well, what happens if I change this parameter by a little bit? Well, you just go to your exact answer, put in the new value for the parameter, and see what comes out. How many of you are econ people? So in a lot of the economics models, you no longer have closed form answers. You have to do huge Monte Carlo simulations. You run things millions and billions of times, hopefully. And you try to get a sense of what the answer will be. And then if you change the parameters, then you run the model again. And it's a little bit harder to see how will things change. It's nice if you can have a closed form answer. All right, so what we want to do is we want to now calculate the probability density function. So x is a random variable. Its probability density function, PDF, is the following. So fx of x is the probability that x equals little x. And here I'm going to assume x is discrete. All right, you always want to choose good notation. So what does it mean to calculate the probability that x equals x? If I want to expand this out, it's the probability maybe of all omega in omega such that x of omega equals x. Think of it as I want to calculate the probability of all the events in my outcome space that have 3 heads. Okay? I like to put the subscript f over here, the subscript x over here to remind myself that this is a random variable, that this function is associated to the random variable x. The more variables you have in play, the easier it is to get confused as to what goes with what. And so if you have multiple variables in play, when you put these on the subscripts, it gives you a sense of what's going on. The next thing we want related to this is the cumulative distribution function. So the cumulative distribution function, the CDF, is the probability you get at most x. And so this would be big F of x would be the probability that x is less than or equal to little x. What does this notation remind you of? The integral. When we did calculus, we used capital letters to denote the antiderivatives of the lower letters. And this is setting us up for when we get to continuous random variables. So we could do it on continuous. So let's say I have some function like this. I'm going to say the probability of an event, the probability x takes on a value between a and b, is the area under the curve from a to b. So the probability that x is in the interval a, b is going to be the integral from a to b of the density fx of x dx. And this is, as I said, this is why we care about calculus. Calculus allows us to compute areas. These areas are probabilities. Can I choose any function as a density? Yes?
I don't think you can choose a function that has like a total area greater than 1.
So we can't have total area greater than 1. And in fact, could we have a function whose total area is less than 1? No. So we need two things. So the first is we need the integral from minus infinity to infinity of fx of x dx to equal 1. This is not quite enough. We need one other thing. Yes?
Function wants to be non-negative.
So we also need fx of x to be greater than or equal to 0. All right. Do we have any ringers in this class who have taken measure theory and seen the Lebesgue integral? Okay, good. So if I change the value of my function at this one point and make the function -2 over there, am I going to change any of the integrals under the curve? No. Because the area of a singleton, it's just that line segment. That line segment has no area. I can change the value of my function at finitely many points. So technically, I could allow it to be negative at finitely many points. We're not going to look at anything like that. Okay, you can drop this. In advanced measure theory, they talk about a more general integral than the Riemann integral. This is the Riemann integral. There's better integration methods out there. This is good enough for what we're doing. And what we really don't care about is, you don't care what's going on a set that basically has no length. So you can actually show that the rationals have no length in the interval 0, 1, that there's very few rationals. And so I could redefine my function to be -2016 at all the rationals, and I would not change the area under the curve, but I would have to use a more advanced theory of integration. I really don't want to go through that. You don't want me to go through that. We all agree. So we're going to just use Riemann integrals. I'm going to just say I have a function that integrates to 1, and it's non-negative. And these will be the set of functions we look at. You could also look at mixed distributions, where the random variable maybe it has a discrete part and a continuous part. So maybe I have discrete probabilities of 0, 1, 2, 3, and then I continuously have probabilities from 5 to 7. I'm not going to really look at something like that. You can combine the two situations like that. Okay, so this is going to be my way of calculating probabilities. We will just integrate under the curve. And so similar to before, we say f of x is the PDF of x, and big F of x is its CDF. And so big Fx of x would be the integral from -infinity to x of fx of t dt. So one of the common mistakes is if I want to evaluate the CDF at x is to have x as my dummy variable. I can't have x as my dummy variable because that's where I want to evaluate things. If I wanted to, could I use a smiley face as my dummy variable? Yeah. The mathematicians would laugh at me, but can I use it as a dummy variable? Absolutely. The only thing I can't use is I can't use the letter little x because little x is the upper bound of integration. I want to calculate the probability I take a value at most little x. And whatever I put in here, I integrate out. So Over here, I will use the letter t. There's a lot of theorems you can prove about the cumulative distribution function. One of the things I try to emphasize always is to look at extreme cases. What are the extreme cases for x? So what would be the extreme cases? Yes?
With x equals infinity.
X equals infinity. So we could take the limit as x goes to infinity. So what should this go to? 1. You know, something happens, right? And we've defined our probability distribution, so if we integrate from minus infinity to infinity, we get 1. So the limit as we go off to infinity should be 1. There's another extreme case we should be able to get. What's the other extreme? Negative infinity. So what should be the limit as x goes to negative infinity? 0. So it should start off at 0 at negative infinity and slowly rise all the way up to 1. And then you can prove lots of different results about, when is the cumulative distribution function continuous, stuff like that. We're not going to get into too much of this in this class. This is a first course in probability, but as you're trying to make things rigorous, as you're looking at convergence, these are various things. The idea is to always be thinking when you have a capital F that this is coming from a antiderivative. Now we will see later in the semester that there will be times when we will need to integrate functions that do not have a closed form antiderivative. And we will find a way to do it. And so obviously we can't just be ending at their antiderivative. It'll be an intermediate step to the answer. And so one of the nice things is theoretically we can just write down big F of x and just work with it. If we had to use it, that would be different. But for a lot of the arguments, we just need to know that there is some function big F. What it actually is not going to matter. What do you think we'll be doing to the big F at some point in the argument? What do you think we'll probably have to do to it to make it nice? Take the derivative. So in a lot of the arguments, the big F will vanish by the time we get to the point we care about. And it will be just used as a helping step in the argument. So this is just giving you a little flag to alert you to what's coming down the pipeline. So we will be seeing some big F's when we do some change of variables. You've all taken linear algebra, or if not, you're supposed to nod now because that's a prerequisite for this class. So one way to view linear algebra is it's the subject about changing variables. And depending on what problem you have, different coordinate systems are better than others. We will often want to change variables. If I give you one random variable, I might want to have a function of a random variable. Maybe the amount of money I give you is a function of the number of heads. And so we maybe have a kind of gambling game. And I want to know, well, how would my new variable, what would its probability density function be, given I know the probability density function of the input random variable? So if you just think about it, if you know the probability density function of x, should you be able to figure out the probability density function of x squared? Yeah. There should be a way to do that. There should be a nice way to compute that. And that's going to be one of the goals. How many of you remember Calc 3, multivariable calculus? How many of you remember the change of variable formula? Is there any hand up right now? Wow. An OFA. Nobody remembers the change of variable formula? Do people at least remember that there is such a thing as the change of variable formula? Okay. Do you remember maybe the change of variable formula in nice cases, polar coordinates? Circles, right? R d theta, which should really be dr r d theta, but we'll deal with that later. Then there's change of variables for spherical coordinates, change of variables for cylindrical coordinates. And if you had a truly inspired teacher, they might talk a little bit about the general form of the change of variables, but probably not. We will have something like that. How many of you remember the change of variable formula for the sphere? How many even remember the spherical change of variables? Just what the variables themselves are. The rho, the sines, and the cosines. Are you also a physics major?
No.
Oh, okay, excellent. Chemistry? Outstanding. All right. And was your hand up? Yes? No? Okay. So most people have forgotten the change of variable formula, even just what the variables themselves are when you pass from Cartesian coordinates to spherical coordinates. For some of the problems, we're actually going to have to use the n-dimensional sphere. I will show you tricks later in the semester to bypass having to know what the change of variable formula is and how to bypass writing down what the change of coordinates are. There's a great way to avoid all of these. So one of the big themes I want to show you is how you can use symmetry to your advantage to eliminate a lot of these calculations and reduce them to one-dimensional calculations of things you've seen. But the change of variable formula is one of the two big techniques we have in multivariable calculus. There's one other big technique we have for evaluating integrals, or multiple integrals. Anybody know the other technique? Yes? Changing the order. That's basically all of multivariable calculus, or at least the integral side. Change variables or switch the order. You cannot always switch the order. Sometimes it fails, but it's a great thing to try. Okay, so let's consider the following. Just want to make sure I do the same example from the book. I'm going to give you the function f of x equals 2 plus 3x minus 5x squared, 0 less than equal to x, less than equal to 1. Okay. So I have a niece named Justine. She's almost 3. I saw her this weekend when I went to the hockey conference in Boston. I think she said that this was a probability density function. It's hard to tell because, she doesn't really say that many things other than bouncing and jumping. But I think she claimed that this was a probability density function. What can I do? I'm sorry? So one thing is I can integrate this. What else can I do? There's 2 checks. One is to see if it integrates to 1. What's the other check? Yes? Is it always positive? I think it's easy to quickly look at this and see, is it always positive? So when you see something like this, how do you tell if it's always positive? Yes?
You look at the leading term, so in this case it would be -5x squared.
Okay. So if x gets very large, this is going to be negative. The problem is x only goes between 0 and 1. Now you can factor this. So I think it's, so I've got to have a 5x here and an x here. So I want to do this. And then I want to get a 2, so I've got to have a 2 and a 1. Right? So I think I've got to put the 2 here and the 1 here. I want to have a +3, so I think I want to have a plus and a minus. So this will give me 2 minus 2x plus 5x is plus 3x minus 5x squared. And now this is very easy to see that this is going to be greater than or equal to 0 in the region we're looking at. So the function is non-negative. Now we have to integrate. Which should we integrate, this function or the factored function? I'm sorry? Yeah, the top. The top is much easier to integrate, right? The factored function, I would not want to have to integrate that. So if I integrate from 0 to 1 of f of x dx, this is going to be the integral from 0 to 1 of 2 dx plus 3, the integral from 0 to 1 of x dx, minus 5, the integral from 0 to 1 of x squared dx. So I get 2, I integrate this, I get x squared over 2, which is 1/2, plus 3/2, minus x cubed over 3 becomes 1/3, so minus 5/3. And I think when the dust settles, we get 11/6. Okay. Is this a probability density function? No. This does not equal 1. So unfortunately, Justine was wrong. No, I mean, she's not even 3, so it's understandable. How long is she? Is she horribly wrong? If you had to choose a condition to fail, which would you rather have fail? The integral is 1 or it's negative in some place? Yeah, the integral. How can you fix the fact that the integral is not 1? Yes? Yeah, divide by whatever the integral is. So if we consider g of x to be f of x divided by 11/6, which is the same as 6/11 fx of x, this will now integrate to 1. So now it's a density. We will see later in the semester in absolutely amazing ways the fact that if I have a probability distribution, what must it integrate to? 1. So we will write down some extremely painful integrals, but I will know it's an integral of a probability density. What must it equal? We will use this to calculate some extremely hard integrals that would be a pain, that you would have to use these multidimensional change of variable formulas. But because it's a probability density function, this is in some sense, it's called the theory of normalization. It has to equal 1, and we get the answer for free. So if I have something that's non-negative and it integrates to something other than 1, can I always fix it? Usually. When can I not fix it? There is a situation where if it's non-negative, I can't fix the integral. So if it integrates to 0, I'm dead. Okay, what else? If it integrates to infinity. So if the integral is 0 or if the integral is infinity, we can't fix it. But anything else, we can just renormalize. Okay, any questions about this example? All right, everybody's comfortable with this? Okay. What I want to do now is I want to go and look at rolling a fair die. Okay? How many of you have played games like Risk, Monopoly, games where you roll die, okay? So if you roll 1 die, it's not that hard. If you roll 2 die, it gets a little bit more interesting. As you start rolling more and more die, it becomes fascinating. If there's anybody who's a Dungeons and Dragons fan here, we're not using your die today. That gets too interesting. So we will consider a fair die. So xi is the roll of a fair die. And now what's nice here is we don't really have to worry, gee, with the coin, let's make a head 1 and a tail 0. I wonder what I should make a roll of 5 equal. It's quite clear what the value of the random variable should be in this case. It's just the outcome. So now let's let yn be x1 plus xn, the roll of n fair die. Okay? What's the easiest value of n to study? 1. We're going to assume they're all 6-sided die. It's how many die. The easiest is when there's only 1 die. So the probability yn equals k is equal to 1/6 if k is in 1 to 6 and 0 otherwise. Okay? So this is a discrete uniform random variable. It's not continuous, and it takes on 6 values, and each value has the same probability as the others. Uniform random variables are extremely common. They're very nice and easy to work with. All events are equally likely. So then the question becomes, what would the probability of y2 look like? So if I now roll 2 die, what would I expect? Anybody know what the shape would be? So I roll 2 die. Triangle. So probability of y2 So what we're saying is uniform plus uniform is triangle. Okay? So how would we calculate these probabilities? What are the possible values of k? I'm sorry? 2 to 12. And what I want to do is, I care a little bit about the probabilities of rolling some fair die, but I care more about the method. And there's going to be some really good techniques in this method that you can use for more complicated problems. Okay? What's the easiest number to calculate? 2 and 12. So let's do 2. What's the probability of 2? Okay, so if k equals 2, what's the probability? 1/36. We have 36 possibilities, and each possibility is equally likely. If we have k equals 3, what's the answer? 2/36. If we have 4, 3/36. 5 is 4/36. 6 is 5/36. And 7 is 6/36. The way to look at it is, let's say I want to calculate the probability of a 5. What are the possibilities for the first die? 1 through 4. And then the fifth die is determined. And there will always be the second die is determined. There will always be a value of the second die that works. So if my number is less than 7, once I choose the value of the first die, there will always be a value of the second die that works. It'll be uniquely determined. And that's why I have 1 less. Now let's say I want to calculate what's the probability I get 8. How would I calculate the probability I get 8? So how should we do 8? Why is it the same as 6?
Because the number of ways to be 4 from your maximum is the same as the number of ways to be 4 from your minimum.
Good. So the number of ways to be 4 from your maximum is the same as the number of ways to be 4 from your minimum. So we want to look at things a little bit symmetrically. Let's let Wi be 7 minus xi. You should think of Wi as the complementary roll to your ith row. So if you roll a 2, then Wi would be 5. If you rolled a 6, Wi would be 1. Okay? What are the possible values of Wi? So what are the possible values of Wi? 1 through 6. What's the probability Wi equals 4? 1/6. So the probability Wi equals k is also 1/6 if k is in 1 to 6 and 0 otherwise. So now if you look at W1 plus W2, that's the same as 14 minus x1 plus x2. Hopefully I haven't made any algebra mistakes. This is reasonable. I claim that this has the same distribution as this. That the sum of W1 plus W2, the probability that this equals 3, is that the same as the probability that x1 plus x2 equals 3? These have the same density. They're the same density. There's no difference between the density of W1 and x1. There's no difference between the density of W2 and x2. They both assign values of 1/6 to the elements 1 through 6. So if I want to calculate the probability that this sum is 8, That's the same as calculating the probability that this sum is 6. So because of this observation, once we've done half the table over here, we can fill in the rest. So this is a really nice use of symmetry, is looking at these related variables. We see that by understanding x1 plus x2, we understand w1 plus w2, and we can pass back and forth. So then if you want to impress your friends, can you write the answer in a nice way? The probability that y2 equals k, I probably should have looked at this ahead of time. I think it's going to be maybe 6 plus 7, maybe 7 minus k over 36 for 2 less than equal to k less than equal to 12. So if k equals 7, this becomes 1/6. If k equals 5, we get 6 minus 1 is 5 over 36. If k is 8, we get 6 minus 1, which is also 5 over 36. So here is a nice, clean way to write down the probability density of the die. This is our nice triangle function. And the triangle function, you can see it's related to the absolute value. And the peak is going to be where k equals 7. Okay? Any questions on how we get the sum of two die? Okay, who has played Risk? Okay, if you're playing Risk, what's the maximum number of die you can roll? I'm sorry? 3. If you're on offense and you have at least, I think, 4 armies in a territory, you can use 3 die. Can anybody think of a game where you can roll 4 die at once? Other than Dungeons and Dragons?
Axis and Allies?
Axis and Allies. Okay, good. How many can you roll in Axis and Allies? It's been
Up to as many dice as you have.
okay. And how many? It's been so long since I've played Axis and Allies.
I think the game comes with like 12 dice.
Oh, beautiful. Very large number. Excellent.
Yeah, you can like bring out as many dice as you have used. So
Okay, so here's my question. Which would you rather find? The density of x1 plus x2 plus x3, or the density of x1 plus x2 plus x3 plus x4? Any thoughts as to which one you'd rather do? Yes. First one. Why? Less things to deal with. Anybody want to give me an argument for the second one? I love parentheses. How should I put parentheses here? Oh, yes. How do I put the parentheses?
Do like x1, x2, and then x3, x4.
So if I do it like this, this has the same density as that. And I've just computed this density. I just add that. Now, I mean, it's not horrible here. I already know what this is.
Now you really only have to do one less thing.
So if I now have this, if I want to calculate the density of adding 8, I would have this group like this. I would group them together, and then I would group the last 4 together. And I would add that density to itself. So later in the semester, we'll deal with how do you find the density of sums of independent random variables. And you'll see that a lot of times like this, it's very useful if you deal with powers of 2. Powers of 2 make things easy. Now, I've been using this word independent a lot. Well, what if the variables are not independent? Assume x and y are not independent. What is x plus y? If you want, assume x and y have the same density. So if I assume x and y have the same density, this is sadly not enough to understand x plus y. One possibility is maybe y equals negative x, and I have some random variable that's symmetric. So the probability I take on the value of 5 is the same as the probability I take on the value negative 5. In this case, what would x plus y be? It would just be 0. Or You could take the case where y equals x. And then what would x plus y be? Twice x. So the situation is extremely different if you have dependent random variables. You need to know how they're dependent. So later in the course, we will do a lot of stuff with dependent random variables. I'm looking forward to no longer having to wear 2 Fitbits, but I'm trying to see how close the dependencies are between these 2 random variables. And so I've got over 2 months of data now. And so if you know what the dependence is, you can often figure out what their sum will be. But in general, if you do not know the dependence, it's going to be very hard. All right, so this is a good place to stop. Remember,